So first question, do you know what the graph of a weak acid titrated with a strong base looks like? It's kind of hard for you to respond to that one. So I'll just go ahead and draw it. So, or what is the important characteristic of a weak acid titrated with a strong base? What is different between that weak acid titration curve versus a strong acid titration curve? Do you have any idea? Yes, buffer region, very important. Okay. Oh, that's not nice. Not very good at drawing straight lines. And the curve was going to be, so properly pH 14 here, and 0. Curve is going to be like that. Yes. So it has this curved region right here, or probably not there, but here, which is your buffer region. So even though you're adding a great amount of base, it's not really changing. And should be here the ml or volume of strong base added. So it has this buffer region because there it's not really changing, whereas if you had your strong acid curve, it would be something like this. So it doesn't have like that same, like, where it kind of changes at first, like it goes up and then it kind of like doesn't, and then it goes shoots up. So your strong acid, it doesn't really have that curved region. Instead of it being curved, well, it is curved, but like the other way. So that's the buffer region is pretty much the most important part. That's how you can differentiate between the curves. Also, we're moving into question 2, where it talks about the 4 features of the curve. Do you have any idea what the 4 features of the weak acid titration curve are? 4. You don't have to get all of them. And you already got one of them, buffer region. There's also like another difference. Yeah, pH at equivalence point is higher than 7. It's like 7's here, here, and it's like there. And there's 2 other parts. One of the parts also has to do with the fact that it is a buffer, which is that the pH increases slowly as the amount of OH minus increases, which makes sense because it's a buffer. But the other part is that, I don't know if you know the other part, like the difference between the 2 curves. If you look at them from like what I drew, I tried to make it a little more obvious because I was like, I'm not good at drawing. So. Yeah, well, not exactly 0, but it's just that the pH is usually pretty high. It's not 7, but it's not above 7. It doesn't start above 7, but it's like pretty close to 7. Whereas like, yeah, your strong acid is going to be pretty close to 0 because that's how strong they are. So yeah, those are your 4 features. So I'm not gonna write them down. I talked about them. I was like, oh man, I gotta write them down now. But I think I'll just continue to the next one. And the graph of a weak base. I think personally, when I took the course, this always confused me a little bit. Like, I don't know why, but it just confused me a lot. It should have. Not the like the graph is confusing. Like I guess just like because I knew exactly what the weak acid looked like, but I wasn't sure like the wheat base, like what the buffer region looks like is pretty much where my confusion came from. So like I guess in my head I imagined it to go up and then down, but that doesn't make any sense because it would have to go like a curve down. That. Yes, so it should be pretty pronounced curve like that. Yes. So that's what your weak base. I didn't need to put this here, but I just felt like it. And then yeah, your equivalence point is going to be below 7. Going to be below 7. Okay. Ask me a question. I'm gonna stop the screen share for a bit. Answer her question. So, and start. Okay, so the next question is, what is the pH of a solution of 0.53 molar? This time I do have my calculator. Every time I forget. So, do you know the first step in determining your pH of this solution? I think I put this question here intentionally to see if you knew what to do. Any ideas? Okay, if you don't. Okay. So the first step, yes, perfect. Ice table. Make an ice table. That's it. Yeah. So the first step is making your ice table. So what you're gonna do first, write out the equation plus water, and I noticed I didn't put the phases, but that's okay because you kind of got it down by now. So I E is like a little refresher. So you got 0.53 matter minus x plus x is 0, 0 plus x. Then we got 0.53 minus x. So your Ka equals x squared over 0.53 minus x. So your Ka is slightly less than 10 to the 4 or 4 magnitudes. So we're going to go ahead and get rid of the x. It's kind of close, but I'll call it because it's really not, at the end, it's really not going to have that significant of an effect. So, and if you get confused anywhere, feel free to chime in, let me know. So you got your Ka value equals x squared. 1.53. And square root So, some more space. X equals 0.003. So your X is actually sufficiently small enough for it to not really have that great of an effect on this concentration, which is good. So this is molar, and that also is your H3O plus concentration. And you just take negative log of this to get your pH. This is all review. So your pH is 2.5. I'll do 2.52. This is the pH. And 5 pretty much is going back over, it's using 5 uses the same, like the information for 4 use identify. So if you like, that's, I said above solution just to try to make it more clear. Okay, so the first part of the question is, if there is 35 ml of the above solution, what volume of 0.32 NaOH is needed to neutralize the acid? So I don't know if this is probably a good question or if I'm going to ask it properly. But when it comes to acid-base reactions, do you know what unit you need, or what kind of quantity do you need in order to build the relation? Like, what do you need to convert to? One thing specific. You always relate this one thing, this to this, in order to. I'm not sure if this is a clear question, but maybe after, like, if I give the answer, then it'll make more sense. But if you know, then feel free to like say something. But if you don't, then that's fine. Any idea what the relationship is built upon? Okay. So the relationship is mole to mole. That's what I was going for. I hate asking that question because I never feel like I ask it. There's got to be a better way of asking it that makes it clear what I'm trying to say. But yeah, whenever it comes to acid-base reactions, what you're relating is moles to moles. Like, you wouldn't use molarity to molarity. You relate moles to moles is ultimately what you're gonna do, because 1 mole of acid is going to react with 1 mole of base if it's a 1-to-1 molar ratio. Anytime you're doing any kind of reaction, it's always focusing on moles. Like, moles is what 1 mole of this reacts with 1 mole of that. I guess kind of what I was trying to get at. So in order to know how much I need to neutralize this acid, I need to know the moles of acid that I have. And ultimately, do you know at what point do you achieve, does your base neutralize your acid? Like, how much base do you need to neutralize your acid? Hopefully that's a better question. No. Okay. It's just you need the same amount of bulk of base. You need the same moles of base to neutralize your acid. So whenever it has the same amount of moles is when it's been neutralized. So it doesn't matter whether it's a weak base, a strong base, a weak acid, a strong acid. You need the same. They need to have the same amount of moles to neutralize each other. That is, if the stoichiometric coefficients between them are both 1. If it's not one, then it changes. But if it is, then it's the same amount of moles of base acid to neutralize it. Because beyond that point, you will just have the basic species of the acid, but you'll no longer have any more of the acid. So I have 0.53 molar acetic acid. So 0.53 molar. And instead of writing molar, I'm just going to write moles over liter. So it's the same. And multiply that by the amount of acid that I have, or the volume, 0.035 liters. And that's going to give me 0.0185. I'm going to do 1819. This is moles. And I know it's a 1-to-1 ratio, so it's going to be the same amount of moles of base needed to neutralize the acid. So I'm just going to go ahead and divide by the molarity of base that I do have in order to get liters. If I take 0.32 moles over liter, moles cancels, liters goes to the top, and it's going to end up being 58 milliliters. That's how much I would need, approximately how much I would need to neutralize this acid. So then the A part is the pH at this point above or below or equal to 7? Do you have any idea? Kind of answered before in another question. Okay. Well, the pH at pH no, pH would be above 7. This is a weak acid titrated by a strong base. So, like, go back to the pH here, is above 7 here, above 7. 7 right here, and it's above 7. Because it should be basic after. That's because the species that exists after the acid has been completely neutralized is the conjugate base of the acid. So, pretty much like what it looks like. It's going to be CH3COOH plus NaOH, going to react to form. It's going to be a reaction arrow, not an equilibrium arrow. CH3COO minus plus water and like an ion. So pretty much you no longer have at the equilibrium, at the equivalent point, you no longer have the acetic acid, you no longer have the sodium hydroxide, you only have the react or the product. So now you have to determine the pH at the equivalent point. So this is where it gets a little more tedious, because it's like, how do I do that? That's because you know that at the equivalence point, all that exists that is going to contribute to your pH is this species here, this acetate ion. That's all it's going to contribute. So you got to set up another reaction. You got your acetate. Since it's going to react with all the water around it, and this is going to be equilibrium, and it's going to form okay. But first, obviously, you have to determine the volume, or not the volume, the molarity of acetate that we have. You can't just make something come out of nothing. So you know that you started off with 0.53 moles of your acid. So if all of that went to its conjugate base, that means you still have 0.53 moles, which are 0.53 moles of conjugate base now. It all went to acid. All of it just lost hydrogens and it all went to base. So, but now you also have a different volume because at your equivalence point, you have the 58 ml of base that you added, and you have the 35 ml of acid. You got to add those together. It's going to be 93 milliliters, and your 0.53 moles. So it's going to be 0.53 divided by 0.093. Oh, no, I'm sorry. Not 0.53 moles. That's my mistake. 0.19 moles. 0.019 moles. So I was like, that number is way too big. That doesn't make any sense. Okay. Yeah, that makes more sense. And you're going to end up with a concentration of 0.20 in your ice table. And if you need me to work out what I did, please let me know. I will do that. And then water doesn't matter. And it's 0 and 0. Because remember that all of the acetate or all of the acetic acid did get consumed by the base, but the acetate ion is going to go on and reform the acid. So it starts off as 0 because this is the new reaction that you have. This is minus X, 0.20 M, or not M, but it is M, but I'm not going to write it. And then X. So now it's the confusing part because you have your acetate and you have OH. So since you have your OH minus, since you created OH minus, you're going to need your Kb value. So it's going to end up being Kb equals X squared over 0.20. And I'm going to put 0.20 because I know that the Kb is for sure lower or less than 10 to the 4 magnitude. I don't know if it's 10 to the 4 magnitude or 4 magnitude, but I know what I'm trying to say. I'm just not good at saying it. And in order to find the Kb, you know how to find Kb since we do have Ka, and the Ka is 1.75 times 10 to the negative 5. You know how to find Kb. Well, I'm talking about the new info Professor lectured about today during this session. No, generally, I usually talk about like the previous like 2 lectures before, because like if I usually don't do the previous lecture, like the lecture that just happened, because people don't remember, or you're less likely to get like, I guess, participation because people are like, they need time for it to settle into their brain. So I'm not going to talk about it. If you have any specific questions that you want to ask at the end, feel free to, I will answer. If I remember. Yes. No. KW equals 1 times 10 to the 14. Yeah. So yeah, you do find your KD based on your KA. So KW is 1 times 10 to the negative 14. And in order to find your KB, in order to find your KB, you take 1 times 10 to the negative 14 and divide by 1.75 times 10 to the negative 5 is your KA. So you're going to get going to be KB is going to be 5.71 times 10 to the negative 10. That's way smaller than the magnitudes of your. So you're going to have 5.71 times 10 to the negative 10 equals x squared over 0.20. And then let's solve for x. So your x equals 1.07 times 10 to the negative 5, which is your OH concentration. OH minus equals 1.07 times 10 to the negative 5 molar. And then POH going to be the negative log of that, negative log of your OH minus. So this part's a little review. So it should be 4.97, but you're not done yet because pH is 14 minus POH. 14 minus 4.97 is 9.03. So 9.03 is going to be pH at your equivalence point. Hopefully that makes sense. If it doesn't, please let me know. If I was moving too fast, because I'm not too sure about how much of this is review, how much is let's get to new stuff. Okay. So, and this one is similar. It's using the same concentration, so the same 0.53 molar acetic acid. So it says there's 50 ml of the acetic acid solution. It is titrated with 0.25 m lithium hydroxide. So what is the pH after the addition of 50 ml of base? So first, you need to do your little, you know which table we're going to use? Ice table, SRF table. Okay, we're going to use the SRF table. It's going to be plus, I'm going to get rid of the lithium part. Just going to use the OH minus. Going to react on okay, so you're going to have your SRF, meaning that we need moles of everything. Okay, so initially we're going to start off with the moles of acetic acid. So we have 50 ml, and the concentration is 0.53. So that is 0.265 moles And OH minus, we have 50 ml, same amount, or the same volume, times 0.25. So you got 0.0. This is not 0.0265. It should be 0.0265. This is 0 and 0. So it's going to be minus, it's always minus the smaller one. So 0.0125 mole minus 0.0125. Going to be 0.014 moles. So this is going to be 0 moles. Forgot to add on this side. So 0.0125 moles. This, I shouldn't have put H2O because there's definitely not 0 moles of H2O. There's a lot of H2O in there, and you don't count it. Okay, so from this, we're going to, you know which equation we use to determine the pH of, after we do this table, what it's called. People don't know what it's called. Called the Henderson-Hasselbalch equation. Okay, so in this case with the Henderson-Hasselbalch equation, you do not have to convert back to concentration. You don't have to do that because, and there's a reason why, and it's only when you're using weak acid base. When it's strong acid, strong base, you have to. Please do, because if you don't, it's going to be wrong. But the reason why you don't have to is because after you've added your base into the solution, you have the same volume for your conjugate acid as you do your conjugate base. Like the acid and the conjugate base have the same volume. So if I put 0.0125 over 5 ml, just making up a number, and I divide by 0.014 divided by 5, 5 is going to cancel out, and ultimately you're just left with the same amount of moles. So you don't have to include you don't have to convert back to, you don't have to convert to concentration. You can just leave it as is. It's a lot easier, especially if you need all the time you can get. And the pKa of sleep gas, I'm pretty sure it's like 4.7. 4.76 plus log of, it's always the conjugate base over the acid. So your pH was going to be 4.71. A little close. So that's good. Is that good? Yes. I want to say yes. I think I might have made a mistake. The pH is less. It shouldn't be less. It should be greater. Oh, sorry. No, it shouldn't be. I got confused. Doing something different. Okay. So it should be that seems about right. Because that's, I was gonna say, oh, why is it less than your pKa, but we didn't determine the original pH of the solution to begin with. So it can be less than pKa because its pH would have been initially less than because you would have had more acid and less base. So, yeah, 4.71. So even after adding 50 ml of base, it's still like not pH hasn't even equaled pKa yet. So that's like shows you like how effective like buffer solutions can be when you're because when you're adding your base to your acetic acid, you're creating a buffer. So that's why it's like cool because it's like you're making a buffer region. No problem. So yeah, it can be pretty nice. So after you add 100 ml, so it's pretty much the same process. OH minus, act to form H3COO minus plus water. And your moles of acid are going to be the same. Oh, sorry, not ice. I'm just used to writing ice. Not ice. Technically, it's kind of the same thing. It's just that I use like equilibrium concentration. That's not correct. Yeah. So 0.0265. But your moles of base should be different. So you get 0.1 times your concentration of base, which is 0.25. We get 0.025. This should be 0. So minus x, or not minus x. Whoops. Minus 0.025. Always subtract by the smaller one. Always add the smaller one as well. So you're going to end up with 0.015 moles 0 and 0.025 moles. So it's the same process, kind of. Well, it's the same process as before, just different numbers. So you get your pH equals 4.76 plus log of 0.025 over, yes, over 0.015. That's going to give you 4.98. And I calculated the equivalence point of this prior to starting, and the equivalence point is the equivalent volume for adding the strong base. It's 106 milliliters. So after adding 100 milliliters of base, even your buffer or your this is how much the pH has changed. It's not a lot after adding 100 ml. It's still very acidic or pretty acidic. So it's like pretty cool chemistry that it's still not really changing. But let's see, after we add 110 ml, what happens? Okay, so you get same acetic acid plus OH minus reacts to form okay, so it's going to be SRX and 0.0265 again, but this time it's going to be different for your base. 0.25, so it's going to be 0.0275 and 0, and that doesn't matter. So it's going to be minus 0.0265 because you always subtract by the smaller one. So you're going to end up with 0 here, 0.001, I'm pretty sure. 0.0265. So let me verify that. Yes. Okay. So you have, this is mold OH. So pretty much OH minus is a strong base. So you're not really gonna focus on any of the acetate. It's really not gonna contribute that much to pH. Especially with a Kb value of like 5.7 times 10 to the negative 10, it's really not gonna have that great of an effect on the pH, especially not as much as OH minus will. So your initial volume, first we need to determine the concentration of OH. So this is where we're going to add in our C here. Because when you end up with a strong base or strong acid at the end, that's when you need to get the concentration. Otherwise, it's going to be wrong because you can't use Anderson Hassel vacuum. So you started off like 50 ml of acetate or acetic acid. So you end up with, you added 110 ml of base, so you're going to have 160 ml. So in order to determine the concentration, divide moles by volume. So your concentration is 0.00625 big M. Okay. So we're trying to determine the POH first. POH is going to be negative log of that concentration. 2.20. So pH is 14 minus 2.20, which is 11.80. So even after the equivalence point was 106 ml. So after adding only 4 ml past that equivalence point, the pH shot up significantly, which is pretty cool. So moving on to the last part. What is the pH of 30 ml of 0.35 NH3 or ammonia? So you have, I put the constant or the volume in this part of the question first as a means of like little extra information where you still know what to do. So you don't actually need this. Not for this part. For A, B, and C, you do. So NH3 plus water, you're going to need an ice table. It's going to form NH4 plus OH minus. So that's a reaction that is going to have, you have your ice table. So it's going to be 0.035 molar water. So it's not count. And 0 here, 0 there, plus x minus x. So 0.35 minus x, and then x. So Kb equals 1.75 times 10 to the negative 5, which equals x squared over 0.35. I'm not going to use the minus x part because, again, you know, it's a little too small, just a little bit, but we won't count in this case. So solve for x. X is going to equal x is going to be 0.0025, which again would have been a lot smaller. It wouldn't have had that significant of an effect on your NH3 concentration, so you didn't use it. So this is also your OH minus concentration. Okay. I wonder what happened to the. So find the pOH. Going to be negative log of that. So 2.61. So your pH going to be 14 minus that, which is 11.40, or sorry, 39. So that's your pH of this weak base solution. Okay. So what is the pH after the addition of 20 ml of 0.24 m nitric acid? Okay. So have your Na plus NO3 minus, or no, not minus. Going to react, form NH4 plus NO3 minus, which is just an ion. So this is one of those special cases where you don't form water, which happens. So you're going to do your SRF table. So the moles of NH3 we have, so it's 38 ml of 0.35 solution. So it's 0.0105 moles, and you have 20 ml of 0.24, which is 0.0048 moles. 0 there, 0 there. And it's going to be always minus the smaller one, minus 0.0048, minus 0.0048, plus is going to give you, but I don't think I will, like, just for the sake of, just gonna, because ions don't matter, so I just want to, okay. 0.0105 minus, going to give you 0.0057 moles and 0, and then 0.0048 moles. Okay, so this one's going to definitely have a greater effect than the ones I used before. That's because this one has a greater, like, or not a greater molarity, but a molarity that is closer to the molarity of the base, of the weak base. It's going to change a lot more quickly, where the pH of the I was using to titrate with, if it was like a lot smaller, it would take more base in order to, or more acid in this case, in order to make such rapid changes in pH. Okay, so now it's to the Henderson-Hasselbalch. So pH equals pK plus log of, and this is kind of where it gets a little tricky with it, because Henderson-Hasselbalch is always going to be, no matter what, always going to be conjugate base over acid. Always base over acid. It's never acid over base. It's always base over acid. So instead of pulling from here, you pull from here, because NH3 is your base. So 0.0057 over 0.004. So never be fooled. It's always. It will never change. And your pKa is, you can solve for that because you're given the Kb. You can solve for your Kb using Kw, dividing by 1.75, -5. So KB is, I'm sorry, not KB, your KA is 5.71. So take negative 9.24. So it's, replace that, 9.24. So 9.24 plus log 0.0075 divided by 0.0048 gives you 9.32 as your pH after your addition of all that acid. It still hasn't had that significant of an effect. So what is the volume at the equivalent point? So you have 30 ml of 0.35 and base. So automatically always equivalent point, you're always equating most moles no matter what. Always most moles, doesn't matter whether it's strong or weak. You don't need an ice table for this because it's going to, your acid is going to react with the weak base. And even though the acid or the base is going to be consumed and all you're going to be left with is going to be its conjugate acid species, you don't need to do any ice table. It's just always most moles, no matter whether it's strong. So the moles, again, are NH3 0.0105. So at the equivalence point, the moles of acid equal moles of base. That's also important. I feel like I've never covered that. So in order to determine the volume of Na or HNO3 or nitric acid, you divide by its molarity. Hopefully that makes sense. 0.24. This is moles. This is moles per liter to make it easier. So moles cancels. Moles and liters comes up. But I'm going to convert back to ml. So it's going to be 44 ml. So, and now that you know this, or actually for this, I'm going to be pretty exact. Because it matters. 43.75 ml. Okay, so now to find out the pH at the equivalent point. So now you need to do a sort of table. Yeah. 4 plus, minus. So S and you have 0.0105. And you have also sorry. You can do this. Probably shouldn't do an SRX table because you're kind of going to get nowhere. It's going to be there. It's going to completely react. That's kind of just like doing extra. Okay, so you know that all of your conjugate base is going to react to form conjugate acid. So the moles of conjugate base is going to be equal to the moles of conjugate acid, which is NH4. So, but now you need to determine the concentration of it because we're going to do an ice table. So all of the remaining, or all of the NH4 that was formed is going to reform NH3, NH3 in water, or NH3 and H3O plus. So you need to determine your initial concentration of NH4 first. So it's the same amount of moles, but you have different amounts of volume. at the equivalent point. So you started off with 30 ml of your base, and then you added 43.75. So you ended up with 73.75, and take that, divide your moles by volume. So your concentration is 0.14, which makes sense because the concentration of base that you initially have a 0.5, so it should be less. And that doesn't matter, so 0 here, 0 there, because remember you're starting off a clean slate because all of the NH3 that was initially in the solution reacted to form NH4, and NH4 and water will recreate NH3. So minus x, 0.14 minus x, and x. So your Ka equals 5.71 times 10 to the negative 10, which equals x squared over 0.14. So we're solving for x. X equals 9.02 times 10 to the negative 6. Is that right? It's a little off, but that's mostly just because I didn't round, but now I rounded, so you go back and you're like, oh, that's not there. So this is your CO plus concentration. Right. So your PA, which is going to be the negative log of that, is going to be 5.05. This is after adding, this is the volume at the equivalent point. So it's basic, acidic, so that makes sense. It should be acidic. Slightly acidic, so that's pretty good. Okay. So what is the pH after adding 60 ml of 8? So one last one. Plus your HNO3 minus, or not minus, I always say that, I don't know why. Minus H4 plus nitrate. This is where the minus comes in. FRF. So still the same, 0.0105, but you should involve your concentration, 0.24 m. So 0.24 times 0.0144 moles, 0, and minus, sorry, always you see the x. So minus 0.0105 minus 0.0105 and plus 0.0105. And again, that's not relevant to calculating pH. So this should be 0. This should be 0.0039 moles. And this should be 0.0105 moles. But you have now reformed like very strong acid. So NH4 is really weak, so it doesn't really do anything. Like, or it does, but it doesn't contribute to pH significantly the way that HNO3 will, because HNO3 is a strong acid, so it's going to completely dissociate. So this is where, when it comes to strong acids, strong bases, is where you need to add the C part, because you need to determine concentration. So you had initially, you had 30 ml and you added 60 ml, so you have 90 ml. So take that divided by, you have a concentration of 0.043 molar, and I'm not going to do NH4 because it's not going to be useful for calculation. So pretty much all of the HNO3 going to go to H3O plus. So we can just solve for pH using the HNO3 concentration. So 1.3, that's your pH. After adding 60 ml, only is not that much greater than the equivalent point, but it did have a significant effect on your pH. That's all I have for today. Please make sure you guys check out the paper on the section 4 list of concepts to go over, because the test is going to be Friday/Saturday. So please check that out and make sure that you go over it. Also, if there are any questions about the new info that was lectured today? Okay, so I'm going to happy studying.